Hello everyone, welcome to IGNOU Dost. So in this second video of introduction to matrices, we will learn about the second half of the topics that we haven't covered so far. So we will talk about multiplication of two matrices. We'll talk about the transpose of matrice. We'll also see symmetric and skew symmetric matrices, right? So we'll see the bunch of concepts that we haven't explored in the first video, and this will be a bit of advanced sort of things, but they'll be easy to understand. It's just that these are the secondary level of things that we need to understand to get a complete idea about matrices, right? So we'll jump into the slides. So coming to the topic of multiplication of two matrices. So if A and B are two matrices, right, which are said to be conformable. So conformable in the sense, yes, they are in a position to multiply, or we can multiply them for the product AB. If the number of columns in A, that is called as the prefactor, should be equal to the number of rows in B, that is called the postfactor. Otherwise, non-conformable for multiplication. That means the multiplication cannot be done between those two particular matrices. Thus, AB is defined if number of columns in A is equal to number of rows in B, and BA is defined if number of columns is being equal to number of rows in A, right? So let A be a matrix with m rows and n columns, and B be a matrix with n rows and p columns. Okay. Then the product AB is defined as the matrix C with m rows and p columns. Okay. So whatever be the number of rows in the uh, first matrix of the product will be taken, and whatever be the number of columns in the second matrix will be taken, and that will be the order of the product matrix. So that is M cross P, where Cij is basically Aij, Bjk. Ij is equal to 1 to n. Okay. So that is equal to AI1 B1k plus AI2 B2k plus AI3 B3k, so on till AIN Bnk. So that is I throw first number, first I throw first column, and I throw second column, I throw third column of A is being multiplied by first row kth column, second row kth column, third row kth column. So it goes on. That is I kth entry of the product AB is the sum of the product of the corresponding elements of the ith row of A, that is the prefactor, and kth column of B, that is the postfactor. So remember, whenever you take the product AB, A will be the prefactor, B will be the postfactor. So for example, if A equal to, this is the matrix 0, 1, 2, 1, 2, 3, 2, 3, 4, and B equal to 1, minus 2, minus 1, 0, 2, minus 1. Obtain the product AB and explain why BA is not different. Okay. So now they're asking us to find the product AB, right? So for the product AB to define, okay, we have discussed for the product AB to be defined, number of number of columns in this A should be equal to, okay, number of columns in A should be equal to number of rows in B. Okay. Now, what is the number of columns in A? There are 3 columns. Okay. And what are the number of rows in B? That is also 3. Therefore, both of them are equal. Therefore, we can actually multiply them. Okay. We can define the product A. But how do we multiply the elements? So so this is how it is, right? Row 1, row 2, row 3, column 1, column 2. So take the first element in the first row of the A, multiply with the first element in the first column of B. Okay. So these two you multiply. Okay. And then what will be the second element? What will be, so this element is what that will get R1 C1. And to get this element, multiply this second row first column with the first row first column of the B. So it's this. And how do you get this? Multiply this with this. Okay. That's how you get it. And to get the next this element R1 C2. So for that you multiply with this, and you multiply with this particular thing, and you again multiply with this particular thing. Okay. So if R1, R2, R3 are the rows of A, and C1, C2 are the columns of B, so that is how you get. Okay. R1 C1, R2 C1, R3 C1, and R1 C2, R2 C2, and R3 C2. Okay. So that's how you get the particular element. So corresponding elements, you just need to multiply them. Okay. So we'll see the product now. So this is how it works. So 0, 1, 2. So if you carefully observe, 0, 1, 2 is the first row, and column 1 is 1, minus 1, 2, right? And 1, 2, 3 is the second row in A. that you multiply with the first column, that is 1 minus 1. 2, 3, 4 is the third row, and that you multiply with the first column, 1 minus 1. So that is how the multiplication works. Okay. So this thing multiplies with this thing, and this thing. Add them up. Okay. So that's how you multiply. So, and even coming to here, you get 1 into 1, 2 into minus 1, 3 into 2. Add them up, you get the second element. 2 into 1, 3 into minus 1, 4 into 2. You add them up, you get the third element. So that's how the multiplication is done. So if you go to the next page, this is how you multiply the things, right? So 0, 1, 0 into 1 plus 1 into minus 1, 2 into 2, whatever the value you'll have it here. So the order of this will be 3 by 2. That is 3 columns of A by 2 columns, sorry, 3 rows, okay? 3 rows of A by 2 columns of B. Okay, so that is how we get. Since the number of columns of B is 2 and the number of rows is A, BA is not defined. Okay, so for BA to define, that this number of columns must be equal to the number of rows. But we could see that that is not the case. Both of them are not equal. So that is the reason BA is not defined. Okay, so I hope you people have understood. Going to the next slide. So some properties of matrix multiplication. So associativity, that's the first property. That is matrix multiplication is associative. So for three matrices A, B, C of order M by N, N by P, and P by Q respectively, we can say that AB times C will be equal to A times BC. Okay. So AB is a product of the matrices A and B. And if you multiply the final product with C, you will have the same matrix as if you multiply the matrix A with the product BC. Coming to the second property, distributive over addition. So matrix multiplication is distributive over matrix addition. So for three matrices A, B, and C of order M cross N and N cross P and P cross Q respectively, A times B plus C will be basically nothing but AB plus AC. Okay, so that is distributive over addition. And coming to the identity matrix, for any matrix A of order Mn, there's an identity matrix In of order Nn, and an identity matrix Im of order M cross M, says that Im multiplied by A will be equal to A multiplied by M. That means take any matrix A, and you wanted to find such a matrix that if you multiply that matrix with A, you get the A. So that is nothing but the identity matrix. So if you take a number 2, with what you should multiply 2 so that you get the same 2? It's 1, right? So 1 is an identity. So similarly, identity matrix also exists. There is a question here. So if A equal to 1, 2, 3, 4, B equal to 1, 0, 2, minus 3, C equal to 1, minus 1, 0, 1, then show that AB times C equal to A times BC. So this is the cross-checking of associative property, right? Associative, associativity, right? Associativity. So that is what they're trying to check. So how do you find the AB? So as said, R1 C1. Okay, you get R1 C1 here, you get R2 C1 here, you get R1 C2 here, and you get R2 C2 here. So what is R1 C1? 1 2 1 2. Okay, so this is it. So 1 into 1 plus 2 into 2. That is 1 into 1 plus 2 into 2. So that is actually equal to 5. So that is the reason we have 5 here. And coming to R2 C1. So that is 3 4 and 1 2. So if you multiply, you get 3 plus 8. That is 11. So that's the reason you have 11 here. And coming to the next one, that is R1 C2. So that is 1 2 and 1 0. So you have 1 plus 2 into 0. So that is 1. So sorry, minus 3, right? So 0 and minus 3. So if you do it, you get the answer to be minus 6. So you have minus 6, and finally you'll be having minus 3. Okay. So that's how you'll get the value of AB. Similarly, now ABC is multiply this product AB with C. Okay, and the multiplication is valid because what are the number of columns here? 2. What are the number of rows in C? 2. Both are equal. So that is the reason you can multiply both of them. So if you multiply, this is the matrix that you're going to get, right? And so the same will be the matrix. If you calculate BC, the product BC, you'll be getting this. And if you multiply that with the A, you'll be getting this. So yes, both of them are same. So that is AB times C will be equal to A times BC. So the associativity is maintained. Coming to the next thing, calculate B plus C. So how do you calculate B plus C? Just add the corresponding elements. So 1 plus 1, that is 2. 0 plus minus 1, that's minus 1. 2 plus 0, that is equal to 2. Minus 3 plus 1, that is equal to minus 2. Okay, so just add the corresponding elements. And calculate A times B plus C. So A times B plus C is basically, so you have got A B plus C. Just multiply A with that. So again, R1 C1. This is R. This would be R1 C1. This will be R2C1. This will be R1C2. So this will be R2C. Just that. And if you do it, you'll be getting this following one. Coming to calculate AB plus AC. So that we have calculated AB before, we have calculated AC before. Just add them up, and you'll get the same matrix as A times B plus C. So yes, it is distributive over addition. Okay. So it's distributive over addition. And coming to the last one, identity matrix, you can consider 1001. The reason why are we considering it is because we have A to be a 2 by 2 matrix. So consider I to be also a 2 by 2 matrix. So when you consider I to be 2 by 2, you'll be having 1001. If it's I is a 3 by 3 matrix, you'll be having 100, 010, 010, 001. Okay. So all the diagonal elements will be 1, right? So that is the identity matrix. So first calculate AI, we'll be getting the same A. Calculate IA, we'll be getting the same A. So therefore, we can say that I is an identity matrix. Coming to the next concept, that is transpose of a matrix. So let A be a matrix that is of order m by n, and the matrix obtained by interchanging the rows and columns of A is called the transpose of a matrix. Okay, so transpose of a matrix A is denoted by A bar or A T or whatever it is. Okay, A power T, or you can just say AT. Okay, so in other words, if A is a matrix that is having m rows and n columns, then A bar or AT is a matrix that is called as transpose of the particular matrix A, and it will have n rows and m columns. Why? Because we are interchanging the rows with the columns of the particular matrix. Okay. So if you carefully observe here, in this particular thing, we have 3 rows, 4 columns. In A bar, we have 4 rows and 3 columns. The reason being, what is the first row here? 2, 3, 4, 5. So that will be the first column of A bar. What is the second row here? -2, -1, 4. That will be the second column in the A bar. If you take the third row, that's the last row, that is the 7531, that will be the third column in this particular A bar. So that is how you construct the transpose of a particular matrix, right? So I hope you people have understood. Now some of the properties of transpose of a matrix. Let A bar be the transpose of A, B bar be the transpose of B, then A bar of A bar of bar is equal to A. That is transpose of a matrix. Okay. So this is basically transpose transpose of transpose of a matrix. Okay, so you take a matrix, take the transpose of it, and once again take the transpose of it, you'll get the original matrix A. Okay, and A plus or minus B whole transpose is basically A transpose plus or minus B transpose. So if you add two matrices and take the transpose, or you first take the transpose and then add them up, you'll get the same result. A times A whole transport is basically A times A transpose. Okay. So whether you multiply a matrix first with a constant and then take the transpose, or once you take the transpose and then multiply, you'll get the same answer. Coming to the fourth point, AB whole transpose is basically B transpose times A transpose. Okay. So if you multiply two matrices and then take the transpose, this is basically equal to initially taking the second matrix transpose and then multiply with the first matrix transpose. Okay. So this is how it goes. Even if it's like it's a long theorem, A, B, C, D, E, F whole transpose is basically F transpose times E transpose times D transpose times C transpose times B transpose times A transpose. Right? So this is like reverse. You just reverse them and put transpose to each other. This is how it works. Right. So I hope you people have understood. So you can take this example. We have three matrices A, B, and I. So A is 2301. Therefore, A bar will be 2321,031, right? Because the rows will be the columns and the columns will be the rows. And you can do rest of the operations there just to verify whatever the properties that we have discussed. You can do it on your own manual things and you'll be able to get the same answers on LHS and RHS. Coming to the next concept, that is symmetric matrix. So a square matrix A is equal to Aij of n by n. So we have already discussed what is a square matrix. A square matrix is a matrix where the number of rows is equal to the number of columns. Okay? So if it is not equal, then we call it as rectangular matrix. If they are equal, then we term it as a square matrix. Is said to be symmetric if A bar equal to A. That means even if you like if I give you a matrix A, and if you take the transpose of it, and if you found out the elements are the same, the corresponding elements are the same, that means this whatever matrix can be termed as a symmetric matrix. So for example, you can take this example where A equal to AH, GH, BF, GFC, all these are elements, right? Now what will be the A transpose matrix? So we have AHG here, the AHG will be here. Whatever HBF you have, the second row will be the second column. The third row will be the third column. So if you carefully observe, again the corresponding elements are the same. A is A, H is H, G is G, H is H, B is B, F is F, G is G, F is F, C is C, right? So if you can carefully observe, the corresponding elements are same. Then we can term it this as a symmetric matrix, where the transpose of the matrix is actually equal to the matrix. Okay? So maximum number of distinct entries in a symmetric matrix of order n is basically n into n plus 1 by 2. Okay. So for example, if you're trying to construct a 3 by 3 square matrix, okay, 3 by 3 square symmetric matrix. So the number of distinct elements that you can put as 3 into 3 plus 1 by 2. That is actually equal to 3 into 4 by 2. That is equal to 6. So in total, in the 3 by 3 matrix, we can put 9 elements, right? But in those 9 elements, only 6 must be distinct. Rest of the 3 must not be distinct. They must be one among the 6. Okay, that only then you'll be able to construct the symmetric matrix. Not it's not possible. And for any square matrix A with real entities, A plus A bar is also symmetric matrix. Okay, so you take A, take the transpose A bar, and because these are symmetric matrix, these both will be equal. And now again, if you try to add both of them, what are the new matrix that you find? Let us assume it is Y. So even this will be symmetric. That is Y will be equal to Y. Okay? So that is the particular theorem is in. Very important theorems. Coming to the next concept, skew symmetric. So we have discussed symmetric. So of course there will be something like skew symmetric or anti-symmetric, right? So a square symmetric A is said to be skew symmetric if A bar is equal to minus A. Okay, that means if you take the transpose of a particular matrix, that will be basically equal to the multiplication of the particular matrix times minus 1. The scalar is minus 1. Okay, so then it is known as a skew symmetric matrix. So if you carefully observe, if we put I equal to j, then ai will be equal to minus ai, right? So what are we seeing from skew symmetric matrix definition? Aij will be equal to minus aji, right? Now if I put I to be equal to j, that means diagonal elements we are talking about. So 0 0 1 1 2 2. So diagonal elements. So if I put I, so in a j, I in the place of j, I get aii is equal to minus aii. So from this I get aii equal to 0. That means wherever you have the row and column to be the same, the element at that particular place will be equal to 0. So the diagonal elements should be 0. Okay, so that is the property of a skew symmetric matrix that you can remember. So that means all the diagonal elements of a skew symmetric matrix are 0, but not the converse. Okay, not the converse in the sense that is, assume I've given you a matrix. Okay, I've given you a matrix and I've put all the diagonal elements to be 0, and I'm telling that this is a skew symmetric matrix. I cannot say that. Okay, I even need to verify if for the other elements aij is equal to minus aj I or not. Okay, so I even need to cross check here. So that is what it is saying. Not just because the diagonal elements are 0, the rest of the elements will also be negative of each other. That's not how it works. You need to check it manually. Okay, so that is the definition of skew symmetric matrix. So take this example for A equal to 0 hg minus h0f minus c minus f0, then A bar will be equal to, so whatever the first column is there in the A, that will be the first row in A bar. What is the second column that you have in A will be the second row in the A bar. Whatever the third column you have in A will be the third row in the A bar, right? And this should be equal to minus times the A. So that is what you're getting here, right? And some of the note points that you need to mention. The trace of a skew symmetric matrix is always 0. So what is the trace? We have already discussed. Trace is nothing but the sum of the elements in the diagonal. Okay, and because we have seen the elements in the diagonal will always be 0. All the elements in the diagonal are 0. So therefore, the sum of those elements will also be 0, right, in a skew symmetric matrix. And for any square matrix A with real entities, A minus A bar is also a skew symmetric matrix. Okay, so just like in the case of symmetric matrix, where we have seen if A is a symmetric matrix, then A plus A bar will also be a symmetric matrix. Similarly, if A is a skew matrix, then A minus A bar will also be a skew matrix. Okay, and also the third point, very important. Every square matrix can be uniquely expressed as the sum of a symmetric and a skew symmetric matrix. Okay, so let us assume if I give you a square matrix, that is basically nothing but half times A plus A bar plus half times A minus A bar. Okay, what is A plus A bar? It is a it is a symmetric matrix. We have already discussed, right? So A plus A bar will always be a symmetric matrix. A minus A bar will always be a skew symmetric matrix. Okay, so that we have already discussed. So coming to the next type of matrix, that is orthogonal matrix. So a square matrix A is said to be orthogonal matrix if and only if A times A bar is equal to I. So what is A times A bar? A is a matrix. A bar A is a square matrix. A bar is the transpose of that particular square matrix. And if you multiply the matrix with the transpose of that matrix, and if it is resulting in an identity matrix, then the particular matrix is known as an orthogonal matrix. Okay? So that is very, very important. So if A bar is equal to I, then A inverse will be equal to A. Okay. And if A and B are orthogonal, then AB is also orthogonal. If A is orthogonal, then A inverse and A bar both are also orthogonal. Okay. Very, very important. So orthogonal is very simple. So if I give you a matrix that is square, and if you take the transpose of it and if you multiply both of them, and if you're getting an identity matrix, then you can term that particular matrix as a orthogonal matrix. So if you carefully see in this example, you have this as your A and this as your A bar. If you multiply them, you're getting finally I, which is an identity matrix. So therefore, you can say that A is a orthogonal matrix. So in conclusion, in this unit, we have discussed matrices which help find unique solution to problems when expressed in equations of linear forms. And the basic operation, that is additions and multiplications, we have seen taken up after the introduction of the concept of matrix and types of matrices. And we have seen that matrix defined as a regular array of numbers arranged in rows and columns. There are matrices such as row column matrices. We have seen column matrices like row column matrices and only one row. Column matrices in the sense only one column. And identity matrices, diagonal matrices, null matrices, symmetric, rectangular, triangular, orthogonal. Lot of type of matrices we have seen. And some special matrices like orthogonal and skew symmetric matrix have also discussed in this particular part. Now we'll go through some keywords. Okay. So first one is diagonal matrix. So diagonal matrix in the sense non-zero elements only in the diagonal running from upper left to the lower right. Okay. So take the upper left, that is zeroth row, like first row, first column, to the lower right, that's nth row and nth column. So only in this particular diagonal you will find non-zero elements, right? And the rest of the area you'll only find zero elements. I mean, the elements will be zeros. Okay, so that is the definition of diagonal element, diagonal matrix. Equality of matrices. So two matrices are said to be equal if each matrix has the same number of rows and columns, and corresponding elements within each are also equal. Okay, so if I give you two matrices A and B, and if I ask you to find the equality of them, then A must have the same number of rows as B, A must have the same number of columns as B, and whatever the elements that we are going through A must be the same elements in the B as well. Coming to the next matrix, next keyword, that is identity matrix. So a matrix usually written as I with ones on the main diagonals and zeros elsewhere. Okay, so rest of the area you'll only find zeros. In the diagonal, you'll only find one. Okay, so all identity matrices are diagonal matrices, that you can say, right? Because in diagonal matrix also the same thing happens. In rest of the area you'll find zero valued elements, and only in the diagonal you'll find non-zero elements, right? Coming to the next definition, lower triangular matrix. So a special kind of square matrix with all of its entities above the main diagonal as zero. Okay, so whatever the elements that you're taking above the diagonal will be zero. Only the elements on the diagonal and the below the diagonal are non-zero. Okay. Coming to matrix multiplication. A feasible operation when the number of columns in the first matrix is equal to the number of column rows in the second matrix. Very, very important. So if you're trying to multiply A matrix with another matrix B, then the number of columns in A must be equal to the number of columns, number of rows in the B. Then only you can multiply. Coming to the next definition, matrix, very simple thing, a way of representing data in a rectangular array of rows and columns. Negation of a matrix, so elements of a matrix with the replacement by the negation. So take any element, replace that particular negative element with its negative form. So if there is a 3 in a particular matrix, replace it with -3. If there is -2 in a matrix, replace it with +3. Okay, so change positive to negative and negative to positive. That's it. Orthogonal matrix. So matrix A is called orthogonal if A times A bar is equal to I. So two times it has been repeated. Don't mind. So A times A bar is equal to I. So the product of the matrix with its transpose must result in an identity matrix. If that is the case, then we can term it as an orthogonal matrix. Okay. So coming to the next point, that is rectangular matrix. So a matrix with the number of rows not equal to the number of columns. Okay, if the number of rows are equal to the number of columns, we term it as a square matrix. But in case it is not equal, then we term it as a rectangular matrix. The next thing is scalar matrix. So a diagonal matrix in which all the diagonal elements are the same. So that is the scalar matrix. So Yeah, this an identity matrix is also a scalar matrix. Uh, but the thing is, in scalar matrix, in the diagonal, all the elements are same like the identity, but it need not be one. It can be two, it can be three, it can be anything, right? But in the case of identity, it is. So we can say that all identity matrices are also scalar matrix. Scalar, a single constant variable or expression. Upper triangular matrix, similar like lower triangular. In the upper triangular, all the elements which are all the elements below the diagonal should be zero, and on the diagonal and above the diagonal should be non-zero. Zero null matrix, matrix whose elements are all zeros. Okay, so all the elements on the particular matrix are zero. Coming to the next thing, skew symmetric matrix. So just like symmetric matrix, skew symmetric matrix in the sense a matrix A is called skew symmetric if A transpose is basically minus one times zero. Okay, so to get the transpose, you just need to multiply minus one with the original matrix, then it is known as a skew symmetric matrix. Square matrix, we have already seen number of rows is equal to the number of columns, then it is known as a square matrix. Submatrix, a matrix obtained by deleting some rows or columns or both of a given matrix, right? So if I give you a matrix, delete some rows, delete some columns, and you obtain a matrix, then it's known as a submatrix. Symmetric matrix, a matrix is symmetric if it's equals to its own transpose. Okay, so take a matrix, interchange its rows with columns, and if you get the same matrix again after this operation, then it is known as a symmetric matrix. Dimensions are order. So it is the number of rows and the number of columns in a matrix. Okay. Transpose of a matrix. So new matrix obtained by interchanging the rows and columns of the original. This ends up this particular video. In the next video, we'll discuss the problems related to the matrices.